Hello everyone, I am Siddharthan. Currently, we are in the seventh module of our hands-on machine learning course, and this seventh module is all about building machine learning models from scratch. So previously, we have worked on a linear regression model, and we have seen how we can build a linear regression model from scratch in Python. And currently, we are working on a logistic regression model. And in my previous videos, I have explained you what is the intuition and math behind a logistic regression model and how you can find the gradient descent of a logistic regression model and so on. Now let's incorporate all those concepts related to logistic regression, and we will try to build a logistic regression model from scratch in Python. So we have discussed all about the logistic regression equation, so the sigmoid function, the gradient descent for logistic regression and its derivatives in the previous videos. So if you are not sure about these things and if you are not sure what these topics means, so please refer the previous videos, and I'll give the link of those videos in this video description, so you can watch those videos before watching this one. Okay, so this is our sigmoid equation, and we know that y cap is equal to 1 divided by 1 plus e power minus z, and this z is equal to wx plus d. So this y cap, or you can call this as y at. So y at is the predicted value, the value predicted by our model. So it is nothing but what is the probability that your y value is equal to 1. So we know that we use logistic regression predominantly for binary classification. So binary classification in the sense we will try to classify the data points into two classes, either 0 or 1. So you can think about the 0 or 1 as a person having diabetes or not, or you can think about this as whether a news is real or fake. So you just have two classes, and we want to classify the data points into two classes. And your let's say that our y can take only two values, either it can take the value as 1 or it can take the value as 0. So y cap is what is the probability that your y value is equal to 1. So if your y cap value is equal to 0.8, then that means there is a 80% chance that your y value will be 1. So y cap is a probability, and we know that all the probability values lies between 0 and 1. So your y cap value or your y at value will lie between the range 0 and 1, whereas your y can take only the values 0 and 1, but y cap values lies between 0 and 1. So that is the difference between them, and we know that this z, so z is equal to wx plus b, where w is your weight and b is your bias and x will be our input feature. So what is meant by this input features? So we have already worked on the diabetes prediction in our channel. So I have already made a project video where we try to predict whether a person has diabetes or not, and we have used this data set. So we have multiple columns here, and this final column, this output column, is the target column. So here 1 represents a person having diabetes and 0 represents a person does not have diabetes. So this column is called as the target column, and the remaining columns are called as, so as you can see there are totally 9 columns, and if you just ignore this outcome column, so totally you have 8 columns here. So these 8 columns from A to H, so these columns are called as the features, or you can call them as input feature, and the final column, 8th column, is your ninth column will be your target column. Okay, so totally we have 8 input features here. So these are nothing but your x. Okay, so which I have represented here. So x represents your input feature. This x can be one set of values, so it can be one column values, or it can be multiple column values. So you can think about x as a matrix. Okay, a matrix with multiple rows and columns. If you come here, you will have let's see how many rows we have. So this particular data set contains about yeah, it contains 769 rows. Okay, so it contains 769 rows and 9 columns, and out of that the ninth column is the target column, and the remaining 8 column are the feature columns. So that is represented by x. And the important thing about weight bias is that the number of weight value you have is equal to the number of input features you have. So if you come to this data set, so totally we know that totally we had 8 input features, so you will have 8 different weight values. So you will get one weight value for each column, for each input feature. So if you have 8 feature, you will have 8 weight value, and if you have let's say that we have 20 input features, so in that case you will have 20 different weight values, each for each input feature. Okay, so that is one main thing that you need to note. So this z is equal to wx plus b. So I have already made videos on weight and bias. If you are not sure about this, I'll also link that video as well in this video description. You can watch that as well. So this is our logistic regression equation, or our sigmoid function, and now we need this gradient descent. So the purpose of this gradient descent is to find the best weight value and bias value. So whenever we are using a logistic regression model to fit to a data set, it cannot find the proper weight value and the bias value at one step. So it is a multiple step process. So this weight value and bias value changes depending upon the data set that we have. So our model has to find what will be the best weight value and bias value so that your model can make accurate predictions. For this purpose, we use a gradient descent model or a gradient descent algorithm. So gradient descent is an optimization algorithm used for minimizing the loss function, or you can also say cost function, in various machine learning algorithms. So it is used for updating the parameters of the model. So we know that loss function or cost function is something which is the difference between the true value and the predicted value. So your loss function or the cost function value should be very minimum. So your gradient descent algorithm will try to minimize your cost function value by changing the weight value and bias value. So this will be a multiple step procedure. So it will take some random initial value for weight and bias, and it will try to find your loss function. If your loss function is more, it will try to change the weight value and bias value. Again, it will try to find the loss function and the cost function. So this process will be continued till your cost function value is minimum. So this is called as gradient descent, and the formula for updating weight is this. So w, the updated weight, is equal to, updated weight, so the w in the left hand side is the updated weight, and the right hand side, this w represents the initial weight. So updated weight is equal to previous weight minus alpha into dw. So this alpha is our learning rate. Okay, so similarly we have the formula for bias. So for updating the bias, we have b is equal to b minus alpha into db. So this alpha is called as the learning rate. So as I've told you, the gradient descent will try to change the weight value and the bias value, right, in order to reduce the loss function or the cost function. So learning rate represents how much change do you want to impart to this weight and bias. So that is called as the learning rate. So learning rate is a tuning parameter in an optimization algorithm that determines the step size. Step size in the sense how much change you want to give to your parameters at each iteration while moving toward a minimum of a loss function. So the ultimate goal is to minimize our loss function. So as I've told you, loss function is how much your true value and your predicted value differs. So the difference should be very less. If your true value and the predicted value, the difference between them is very high, that means your model is not making accurate prediction. So we want a minimum loss function. In order to do that, we will use this gradient descent, and this learning rate is the amount of difference you want to give, the amount of change you want to give to your weight and bias. So that is meant by this learning rate. And finally, we have the formula for dw and eb. So dw is nothing but the partial derivative of the cost function with respect to weight, and db represents the partial derivative of cost function with respect to bias. So you can get this formula for dw by differentiating cost function with respect to weight, and you can get the second equation by differentiating the cost function with respect to bias. So these are the things that we have discussed in our previous videos, and now we need these 6 equations: this y cap, z, and this w and b and dw db. So these are the 6 equations that we need, and we are going to write these 6 equations in Python in order to build this logistic regression model. So this is very simple. So we just need to figure out how we can do this. So that's all. Okay, so let's get started with coding part. So I'll just make a text here as importing the dependencies. So importing the dependencies. So we will be using only the Numpy library here for creating this logistic regression. So I'll just make a text here as importing Numpy library. Okay. So the purpose of this Numpy library is to create arrays. So these arrays are called as Numpy arrays. So import Numpy as NP. So we can import this Numpy in short form as NP. So this is the general convention that we use, and most of you would know this. So okay, so I'll run this. So in order to run this cell, you can just press Shift plus Enter. Okay. I'll create a text here as logistic regression. So in this part, we are going to write the code for building logistic regression. So what we are going to basically do here is create a class, and we can name this class as logistic_regression. So you can name this anything you want related to regression, but it should be a single word. Okay, so we should mention parenthesis here. So you can just join this logistic and regression by underscore, or you can just simply remove this, but it should be a single word, and you cannot just have a space like this. Then it will show an error for us. So you can join this with an underscore. So we are creating a class as logistic regression, and within this class we need to mention some functions. So I'll just complete these functions and explain you what this means. So we need 4 functions here. So the first function is the init function, and the second function we are going to write is a fit function, So at the end of each function, you should mention the parenthesis, and within this, we will give the parameters for each of these functions. So the third function that we are going to write is update weight function, update weights, and finally the last function that we need is predict function. So define predict. So let's try to understand what is the purpose of these four functions. So first we have the init function. So no matter what class you are creating, so it can be any object. So in all the cases, we will be using this init function. So this is common for all the classes. So this is basically initiating the parameters for the class that we are creating. So in this case, we are creating a logistic regression function. So similarly in Python, we will create different objects using this class in different cases. And in all those cases, we should mention this init parameter or init function. So this is nothing but the parameters that we want to give to our object. So this will be our first function, and the second function that we have for logistic regression is the fit function. So the purpose of this function is to fit the data set that we have to our logistic regression model. So if you look at our diabetes data set, so we have totally 9 columns, and out of these 9 columns, the first 9 columns are the first 8 columns from A to H. So these are the input features. So based on these features, our model will try to predict the outcome. So outcome value will be 1 or 0, where 1 represents a person with diabetes and 0 represents a person without diabetes. Okay, so these first 8 columns will be our input column and I will be our output column. So we will basically try to fit our data set to this X. So all these 8 columns represent X, and this I column, the ninth column, represents the Y column. Okay, so we need to fit this X and Y to our logistic regression model, and for that we need this fit function. So we will be mentioning this X and Y within this parenthesis, which are the parameters of this fit function. And then we have the update weights. So we know that we use gradient descent in order to update the weights and bias, because we will randomly initiate some weight and bias value, but these weight and bias value won't be the optimum value, so our model won't work fine. So we include a gradient descent algorithm which tries to update the weight and bias by minimizing the cost function. So for this we need this gradient descent model, and for that we use this update weight. So this update weight will keep on changing the weight and bias value so that we get a good model. Okay, so that is the purpose of this third function. And finally we have this predict function. Let's say that we have trained our logistic regression model with this diabetes data. So once the model is trained, if you give all the X values, let's say that we are taking all these 8 X values, and once you give all these values, your model will predict the Y value, which is either 0 or 1. So it will tell you whether the person is diabetic or not. Okay, and that is the purpose of this predict function. So given the value of X, your model will find the value of Y. Okay, so these are the 4 functions that we are going to write within this logistic regression class. Okay, so first we have the init model, which is used to initiate the parameters for logistic regression. Then we have the fit function, which is used to fit the data set to our model, and then update weights, which is used to update the weight and bias value, and finally predict function, which will give us the Y value, whether it is a 0 or 1, based on the X value we are giving. Okay, so these are the 4 functions we need, and let's work on these 4 functions. Okay, so I'll just give you a quick thing about this. So these are the steps involved in a logistic regression model. So the workflow happens in this way. So first thing that we need to do is set the learning rate and number of iterations. So we know that learning rate and number of iterations are called as the hyperparameters, because these are the parameters which are outside the model. Okay, and then we have once we have set the learning rate and number of iterations, then we will initiate the values for weight and bias. So if you see this code here, so we have this init function, right? So within this init function, we will include the learning rate and number of iterations. Okay, and after that we will initiate the weight value and bias value for our model. Then we will build a logistic regression function. So we know that logistic regression function is nothing but a sigmoid function, which I have written here, which is y cap is equal to 1 divided by 1 plus e power minus z, and this z value is wx plus b. So then we will write that particular the logistic regression equation, and after that we need to write the gradient descent algorithm, where we will try to update the parameters of the model. So once this process has been carried out, so we will give the number of iterations. So let's say that the number of iterations that we are giving is 100. So that means our model will go through the data 100 times again and again, and each time it will update the parameters using gradient descent. So once the number of iterations is complete, we will get a proper model which has a best weight value and bias value. So you can change the number of iterations depending on your accuracy score of the model. So we can change this value. So we can change the learning rate and number of iterations value. So once we do that, we will get an optimum model which has best weight value and bias value. So best weight value and bias value in the sense, the model will make good predictions, and it will have a minimum cost function. Cost function means the value predicted by your model and the true value are very close to each other, which means your model is working accurately. Okay, so and finally we can build this predict function. As I've told you, when you give the x value, it will give the output as y value, which is either 0 or 1. So these are the steps that we are going to follow. Okay, so the first step is setting up the learning rate and number of iterations, and then initiating the weight and bias value. Okay, so now let's try to understand what is the importance of class and why we need to create a logistic regression as an object. So we know that Python is an object-oriented programming language, and everything is an object in Python, and we will try to program other things around this object. So again, we are trying to create logistic regression as an object, and in order to create an object, you need a template for that object, and this template is created using this class keyword. Okay, so template in the sense every object has its own characteristics, properties, and functions related to it. So the characteristics and properties of logistic regressions are nothing but this sigmoid equation, the gradient descent, derivatives, etc. So we need to include all these properties and functions within this logistic regression object. So that's what we are going to do. So the purpose of doing this is, so you can also write this logistic regression model without using class and functions. But the reason we are doing this is we don't want to write the logistic regression every time we are using it. Say for example, we are having 10 different data set and we want to use logistic regression for all these 10 projects. So we cannot write this logistic regression code every time we want to implement it. So what we will do is we will create the logistic regression class, and whenever we want, we can use this logistic regression. So it will be like a ready-made code for us. So I'll give you a simple example for this object and class, because this object and class is a very important concept in Python. Let's say that we are creating a car. So the car that we are creating is called as an object. In order to create that car, you need a blueprint for that particular car, or you need a prototype for that car. So in that you may mention that a car should have an engine, and the engine should perform in such way, and a lot of things. So the car should have 4 wheels, brakes, and so on, right? So that template which we are creating for our car can be considered as the class, and the car itself which we are creating is called as an object. So here the object that we are creating is in logistic regression, and the template for it is created by using this class. So that is the importance of class and objects in Python. Okay, so let's work on this. So I'll just give some space here. So the other thing which you need to keep in mind is, so we have 4 different functions. So def represents define, and this is used to implement, in order to write some function in it, and we need to mention some parameters inside this parenthesis. Okay, so when you are creating a class, or when you are creating an object using this class, the first parameter that you need to give within this parenthesis is self. Okay, so I'll create this self, and so it should be given in all the 4 functions. I'll explain you what is meant by this self. Okay, now let's say that we have completed our logistic regression model. Okay, so let's say that we have completed our code, and now we want to implement this logistic regression to fit to a data set. So what we will do after completing it is, so we will try to load an instance of this logistic regression. So how we will do that is, we can create some variable. Okay, so I'll say that I'm creating a variable called as model. So I'm naming this variable as model, and within this model I'm going to load this logistic regression code. So I'll mention this particular name, which is logistic underscore regression. So I'll write here as logistic underscore regression and parenthesis. Okay, so here I'm creating, or I'm loading an instance of logistic regression, and the instance I'm loading is model. Okay, so this is the instance of logistic regression I am creating. And after that, what I will do is, so I will just simply use model dot fit. So here model dot fit represents logistic regression dot fit. So it will come to this logistic regression class, and it will search for the function fit. So if you go through this, you can see that we have the function fit. So this is how the model will work. So we will fit our dataset to this logistic regression model. Now, as you can see here, this model takes the value logistic regression because it is an instance of this logistic regression. The reference of this particular instance is called as this self. So this self and model are, actually they are the same thing. So this self is nothing but the reference of this instance. So we use self because we use it within the class. So whenever you are using, or you are mentioning the instance of the code or instance of the class within the class itself, we call it as self. So this is nothing but the reference of the instance. So you can remember like that. So I'll just remove this. We don't need this. we just need this for the implementation purpose. I just wanted to explain you the purpose of self. Okay, so the self is nothing but the reference of the instance that we are creating. Now we need to mention the parameters within these functions. So as I've told you earlier, the purpose of this init function is to create, or in order to initiate the hyperparameters learning rate and number of iterations. So we will initiate weight and bias separately, but we will initiate the learning rate and number of iterations first, and we will do that in this init function. So init stands for initiation. So I'll just make a text here as initiating, or instead of initiating, I'll write declaring. Okay, so declaring learning rate and number of iterations. Okay, number of iterations. So these two parameters are called as the hyperparameters. So hyperparameters, whereas the weight and bias are called as the model parameters. So I have already made a video on weight and bias and this learning rate and number of iterations. You can watch that one as well. Okay, so we are declaring the learning rate and number of iterations, and as you know, the learning rate is the amount of change that we want to give to our weight and bias. So when we are implementing gradient descent, as I've told you, we will keep on changing the values of weight and bias till we reach an optimum value for these two parameters. So learning rate is the amount of change that we want to give to our weight and bias. So I have given the definition for it here. Okay, so that will be our learning rate, and number of iterations is like the number of times you want your model to go through the data. So these are the two hyperparameters, and let's initiate or declare these parameters. So first is learning rate. So self dot learning rate is equal to learning rate, and self dot number of iterations is equal to number of iterations. So we need to mention these parameters in this parenthesis as well. So learning rate and number of iterations. So you should do this first before doing these two lines. So number of iterations. Okay, so what we are doing here is we are declaring the two parameters, which are learning rate and number of iterations. So when we are loading an instance of logistic regression, say we have completed this code and I am creating an instance for logistic regression as model, and I am loading the logistic regression model. So logistic regression, and within this parenthesis, I need to give the value for this learning rate and number of iterations. So what I will do is I will mention the learning rate as something like, let's say it's 0.01. So you can give any values, and let's say that the number of iterations is, let's say it's 1000. Okay, so totally we have 1000 number of iterations. So this is how we will declare the value of learning rate and number of iterations. So you can manually change these two values, learning rate and number of iterations, and so these two are the parameters of this class logistic regression. And whenever you call this logistic regression, along with this you need to mention the values for the learning rate and number of iterations. So if you just call the logistic regression function, sorry, the logistic regression class without mentioning the learning rate and number of iterations value, your code won't work properly. So you will get an error. So you should mention the parameters which are represented in this init function. So these are so what we are basically doing is initiating the two parameters which are learning rate and number of iterations, and these two are the important parameters for the logistic regression class. Okay, so this is our first step. As you can see here, the first step is setting up the learning rate and the number of iterations, and then we need to give the random weight value and bias value. So let's get into this later, but for now understand that we have set the learning rate and number of iterations. Okay, so we have declared these two parameters. So this will be our first step. So the purpose of this define init function. Okay, so now what we are going to do is the second function that we have is the fit function. And as I've told you earlier, the purpose of this fit function is to fit the data set to the model that we have. The model in this case is of course the logistic regression. So I'll just make a text here as fit function to train the model with some data set. Okay, so in order to fit a function to a model, you need two things. One is the x-axis value and the y-axis value, right? So you cannot fit a model without these two values. So these two values should be there. So the x-axis value is nothing but all these 8 columns, and the y-axis value is the last I column. Okay, so you can call these 8 values as x and the last column as y. Okay, so this is basically is nothing but a matrix. So X is nothing but a matrix, right? So what I'm going to do is we need two parameters here. One is X and the another one is Y. So I'm just taking this data set as an example data set. So once we complete this code, you can use any data set that you have. So I'm just taking this as an example. Okay, so A to H will be X, and last column Y, the ninth column, will be Y. So whenever you are calling this fit function, so whenever you are calling this model.fit function, you have to give two parameters along with it. So one is X and the another one is Y, where X will be your input feature and your Y is the output feature, which outputs either 1 or 0. So this is the purpose of fit function. Now what we need to do is, so there are few things that we need to do within this fit function, and the first thing that we need to do here is determine the number of data points in your data set and determine the number of input features in your data set. Okay, so let's try to understand these two terms. So I'll just remove this, so we don't need this outcome right now. So let's remove this for now. Let's ignore it. So now we have the 8 columns here. So all these 8 columns are called as input features. So as you can see here, we have the number of pregnancies for a woman, what is their blood glucose level, blood pressure, skin thickness, insulin, BMI, diabetes, age, etc. So based on this, our model will try to find whether the person has diabetes or not. So these 8 columns are called as input features. So we can say that totally we have 8 different input features. Okay, and we need to find how many data points are there. So data points in the sense, so each row represents data for individuals. So the second line represents the data for one individual, third line represents the data for another individual, and so on. So if you just go through this data, totally we have about 769 data points. Okay, so as you can see here, so totally there are about 769 data points, and or you can also consider is it as the number of rows. So the total number of data points is equal to the total number of rows and the total number of input features that you have, which is the columns, is equal to 8. So totally we have the data for 769 different people, and the total number of input features is 8. So we can write the shape of this matrix as, so you can consider this as a matrix. So we can write this as, just show you, this is an example of a matrix with 769 rows and 8 columns, right? So ignore the output column, which is the outcome column. So this is the shape of the matrix that we have. Now this first value represents the total number of data points, or you can consider it as the number of rows. So this will be your M value. And this 8, the second value, the number of columns, represent the total number of input features that you have, and this will be N. So M represents the total number of data points. In other words, you can say it is the total number of rows, and 8 represents the total number of input features that you have. In other words, it represents the total number of columns that you have. So it is as simple as that. So this is our X. So X is nothing but the input data. So this is our input data, and our output data will be outcome, which we have ignored for now. Okay, so we need to determine these two values, and for that what we are going to do is, I'm going to mention self.m comma self.n. So M and N are the parameters of this model, of this logistic regression, and as I told you before, we are representing these parameters within this class, and whenever you are doing that, you need to mention self. So whenever you are using this outside the logistic regression, so what you will do is you will represent it as model.m. So if you print the model.m, you will get the value of this m. Okay, whereas whenever you are doing this particular code within the class, you need to represent it by self, as we know that model is nothing but it is an instance, and self is the reference of this instance. Okay, so when you are mentioning it within the code, you need to mention it as self.m and self.n. So we know that m and n are nothing but the shape of X, where the shape of X is 769 into 8, right? So it is nothing but self.m and self.n is equal to X.shape, where your X is all these data. Okay, so excluding the output data, the outcome column, so all the things are X. So when you use this X.shape, it will return an array with the value 769 into 8 when you are using this particular data set. So different data set will contain different number of data points and different number of total number of features. So we can say that there can be another data set which may have let's say that a data set that have 1000 data points or 1000 rows, and it may also have, let's say, 20 columns or 20 input feature. In this case, this 1000 will be your M value. Okay, so I know that this handwriting is horrible, but just tolerate me, I'm not good at this. So this 20 will be your N. So m is the total number of data points or the total number of rows, and n will be your total number of input features. So the reason I'm explaining you this is this value is not constant in all the cases, and this value differs based on the data set that we have. So different data set have different m value and n value, and so we are mentioning it generally as self.m and self.n is equal to x.shape. So when you run this code, you will get the values of m and n. Okay, so that is the purpose of doing that. So I'll mention a text here as number of data points in the data set. So this is actually equal to number of rows, right? So number of rows, and so this will be our m value, and then number of input features in the data set. So this will be the number of columns. So in the example data, diabetes data I've shown you, there are totally 8 different columns, right? So this will be the number of columns, and this value will be our n value. So I'll write this as n. So when you run this code, self.m comma self.n is equal to x.shape. So your m will take this value. So your m will take the first value, which is the total number of data points, and your n will take the second value, which is x.shape, and that second value is the total number of columns that we have. So this is the first step that we are doing in this fit function. Now you may think that what is the purpose of finding m and n? So you may ask that question. Okay, so the reason that the reason for finding this is, if you come to this formula, as you can see here, this is the derivative formula which we need for gradient descent. So dw is equal to 1 by m into y cap minus y into x. Here this m represents the total number of data points. So in order to find this m, you need to run this particular line of code. So if you don't create this line, you won't find the value of m. So this is the reason we are finding the value of m. And the importance of the value of n is that, so we have weight and bias value here. The number of weight value that you have for a model is equal to the total number of input features that you have for a model. Okay, so let's say that we have this data set, and we know that this data set contains 8 input features. So ignore the output column. So apart from the output column, we have 8 input features. So if you have 8 different input feature or 8 different columns, you will have 8 different weight values. Okay, so if in a data set you have 100 different input features, so let's say that you have 100 different columns, in that case you will have 100 different weight values. So each column will have a different weight value. Okay, so that is the purpose of finding the value of n, because so we need to find how many weight values can be present in that particular model. So that is the reason for finding this n value, because n value represents the total number of weight values that we are going to have. And when you are initiating the weight value and bias value, as I told you, we need to initiate the weight value and the bias value. So in order to initiate this weight value, you need to know how many weight values do we have. Okay, so that is the reason for finding the value of n. Okay, so I hope everyone is clear up to this part. And the next thing which we are going to do is initiate weight value and bias value. So initiating weight and bias value. So we will do that by self.w is equal to w. So self.w is equal to np.zeros. So I'll just complete this and explain you what this means. So self.n and self.b self.b is equal to 0, and self.x is equal to x, and finally self.y is equal to y. Okay, so let's try to understand this. So as I've told you, the next step will be initiating random weight and bias value. So we need to initiate some value for our weight and bias, and we generally initiate the value with 0. Okay, so as you can see here, I have for weight, I have represented a Numpy array. So NP stands for Numpy, as we have imported the Numpy library. So np.0 will create a Numpy array with all the values as 0. Okay, and in the parenthesis I have mentioned self.n. So self.n is nothing but, so let's say that in this data set the value of n is 8, right? Because we totally have 8 different columns. So this will basically take the value as np.zeros, in the bracket in the parenthesis it will take the value 8. So this np.zeros with parenthesis 8 will create a numpy array with 8 values of 0. So I'll show you this. So I'll just remove this particular code. So let's create an array as weight. So weight is equal to, let's say that np dot zeros, and within this parenthesis I'm giving 8. So let's print this weight. So np is not defined, so I think I haven't run this particular code. Okay, okay, so we can run this now, and I'll print this weight. Print weight. So this will create a numpy array. So this is an example of a numpy array, and this array will contain 8 values, and all the 8 values will be 0. Okay, so we have given 8 because this data set contains 8 different input features. So in the other example which I have shown you, this particular data set contains 20 different input features, so the n value will be 20. So if you give the value as 20 here, you will get a numpy array with 20 values as 0. Okay, so this is what we are basically doing here. So we are initiating the weight value here. Weight will be a numpy array. It won't be a single value because we will be having multiple weight values which is equal to the value of n. So we are creating numpy arrays with the shape n. Okay, so that is the reason for doing it. Whereas the bias is a single value. So weight is a numpy array. Weight can be considered as an array because it contains multiple values. So you can just consider it as a list. So you can consider weight as a list which contain n number of values, but bias is a single number value. So it is a single real number. So we are just giving the value as 0, whereas as you know, weight is an array or a list. So we are creating a numpy array with all the values as 0. So this self.x represents our input data set x, and this y represents the output column. So the output column is nothing but your outcome column. So this I column is our y, and all the other 8 other different columns are x. So we are representing x and y here. So that's what we are doing here. So this is our next step. So the first step was to initiate the hyperparameters, which are learning rate and the number of iterations, and the second step was to initiate the weight value and the bias value. Okay, so we have completed these 2 steps successfully. Okay, so next what we are going to do is, so now we need to create our logistic regression. Sorry, we are going to create our gradient descent algorithm. So the reason we are doing it here is we are just randomly giving the weight value and bias value as the value 0, but this model won't be accurate because we cannot take weight value and bias value as 0. So now what we are going to do is we are going to create the gradient descent algorithm, so that let's say that we are giving the number of iterations as 1000. So our model will go through the data 1000 different times, and each time it will change this bias value and weight value. So this weight value is 0 and bias value is also 0, we know that, and these values will be changed again and again till we reach point where the model works efficiently. So at this point your model will have a very minimum cost function. Okay, so for this purpose we need to create a gradient descent algorithm, and for this we need to create a for loop. Okay, so I'll just put a text here as function. So sorry, just going to create as implementing gradient descent. So we are going to implement gradient descent here, and the purpose of gradient descent is for optimization. Okay, so implementing gradient descent for optimization, and for this I'm going to create a for loop. For I in range number of iterations, I'm going to update the weights. So self dot update weights. Okay, so this is my next part of code. So let's try to understand what we are doing here. So I'm creating a for loop, and the range of this for loop, for I in range number of iterations. So this number of iterations can be anything. So let's say that we are giving the number of iterations value as 100. So if you give the number of iterations value as 100, so we will do that later in a later part where we will give model is equal to logistic regression of learning rate and number of iterations, as I have told you before. So we will give some number of iterations. If this value is 100, then this for loop will run 100 times. If you give the number of iterations value as 1000, then this for loop will run 1000 different times. Okay, and in each step and in each time your for loop runs, your weight value will be updated. Not only weight, your weight value and the bias value will be updated, and that is the purpose of this purpose of using this for loop. Okay, so now what is meant by this update weights? So we know that in order to update weight, we need these four formulas. So W is equal to W minus alpha into dW, where the W in the left hand side represents the updated weight, and W in the right hand side, this W represents the previous weight. Okay, and alpha is your learning rate, so we know what is meant by the learning rate, and dw is your derivatives, and we have the derivative function here. So dw, and the formula is same for bias as well. So updated bias is equal to previous bias minus learning rate into db, and db formula is this, where y cap minus y. Okay, so this is our gradient descent formulas, and this is the formulas in order to update the weights. And we are going to incorporate all these weights, all these equations, wb equation and dw and db equation, in this update weights function. Okay, so that is the next step which we are going to do, and this process, and this process is called as our gradient descent algorithm. Okay, so and another thing we need before going into that is, so if you see this formula, so let's see what are the values that we have. So we have this weight value. So now the value which we are trying to find is this w, the updated weight and the updated bias. So we will be having this previous weight value. So this previous value is nothing but the value that you have initiated, which is np dot zeros and zeros. Okay, so this is your initial weight, and we also have the learning rate value, because we will while calling the logistic regression class, we will give the learning rate value and the number of iterations value. So you have these values as well. So you have the previous weight, we are trying to find the updated weight, so learning rate value is also there. And now the thing that we need to do is find the dw value and db value, right? And this is the function for formula for dw and db. Here we have the x-axis value, sorry, the x value. The x value is nothing but all the 8 columns, the first 8 columns that we have here. The input column is our x value. If you look at this formula, the one thing that we are missing is y cap, right? So we also have the m value. We have already calculated the m value, which is x dot shape. So self dot m will be your m value, and y is nothing but your outcome column is your y. Okay, so we have all the values in these equations, but we don't have this y cap value. And now the step which we are going to do is find this y cap value. Now what is meant by this y cap? This y cap is nothing but your sigmoid equation. So y cap is equal to 1 divided by 1 plus e power minus z, where z is equal to wx plus b. So the next step would be to write this equation. Okay, so once we write this equation, we can write the dw and db formula, and after that we can write this updating weight functions. Okay, so it is very simple, and I hope you know what is meant by this y cap. So we have already discussed this in our previous videos. So y cap is nothing but, so it is the probability that y is equal to 1. So we know that y can take only two values, and these two values are either 0 or 1. Okay, so we can only take two values, and y cap is what is the probability that your y value is equal to 1. So if you get the y value as 0.8, then it means that you have a 80% chance that your y value is equal to 1. If you have the y cap value as 0.2, then it means you have only 20% that your y value will be 1. So that is the property of this y cap. And the important thing that you know to note here is y cap can have only the values from 0 to 1. Okay, so that's the other important thing that you need to keep in mind. And now we know that this y cap is derived from the sigmoid function, and this z is given by this equation, which is wx plus b. Okay, so now let's try to write this y cap equation. So that will be our next step. So just a second, I'll just have some water. Okay, so let's try to write the y cap equation first, and then we can write the dw and db formulas, and finally we can write the updating weight formula. So that is the process which we are going to follow. So the next step will be, I'll write this as y at, so I'll represent this y cap as y at formula. So this is nothing but the sigmoid function. Okay, sigmoid function which will give you the y cap value or the y at value. So I'll call this as capital Y at. Okay, so y at is equal to, just write this equation. So 1 divided by 1 plus e power minus z. So y at is equal to 1 divided by 1 plus np dot exp, and inside this parameter parenthesis I'm going to mention minus z. Now we need to understand this particular equation. So y at is equal to 1 divided by 1 plus np dot exp. So np dot exp is nothing but your e value, your exponent value. Okay, so e value you can just write it separately as well. I just remove this. Okay, so if you just print np dot exp, your value will be, okay, so I'll just give the value here as np.exp1. So what this basically means is, go to the scientific calculator online. So we know that the sigmoid function has the term e, right? So this e is represented by this np.exp. So if you want to cross check, just go to the scientific calculator and just give e. Okay, so e power. So if you just click this particular button, you will get a power value. Okay, so let's try to check the value of e power 1. So e power 1 is 2.718, and in order to find the e power 1 value, you need to mention np.exp, and inside this parenthesis you need to mention the power which we are trying to give. Let's say that we want to find the value of e power 1, so give the power value inside this parenthesis, and you will get the value of e power 1. And let's say that we want to find the value of e power 5. Okay, so I'll just create text here as e power 5. So you can find this e power 5 value by np.exp, and in parenthesis mention the value as 5. Let's run this, and you will get the value for e power 5, and you can cross check this here. So e power 5. So you can compare these two values. So this is nothing but the e that we have in our equation. So you can find that exponent value by using np.exp, and we have this value within the numpy library. So it is easier for us to write that particular value there. So I'll just remove that. So that's what I have written here. So y at is equal to 1 divided by 1 plus e power minus z, and instead of that e, I'm using this np.exp, which is basically the same thing. Now what I'm going to do is, I'm not going to use z, but instead of this z, I'm going to substitute this equation, which is wx plus b. So your equation will become y cap is equal to 1 divided by 1 plus e power minus wx plus b. So I'm just substituting the value of z here. Okay, so I'll just remove the z, and now within this parenthesis, let's mention wx plus b. So we cannot represent wx plus b as such, so we can write this as self dot x dot self dot w plus self dot b. So this is nothing but the same equation, which is wx plus b. Okay, so I'll just leave some space so that it is clear. Okay, so what we are basically doing here is, so we know that it is wx plus b, but the important thing is w and x are not single integer values. So they are arrays, they are a matrix, right? So the shape of this x is 769 into 8, right? So similarly, your weight value is, it contains 8 different values because it is equal to the total number of input features. So this is basically a matrix multiplication. So this is not the multiplication between two numbers, but it is a matrix multiplication, and hence we are using this dot. So this is nothing but dot represents product of these two matrices. So self dot x into w. So this is similar to, so I'll just write here as this particular part. This second part of code is nothing but it is similar to wx plus b. Okay, so that's what we are basically doing here. So the next thing which we are going to do is, I hope you are clear about what this particular line means. So this is basically this equation. We are just substituting the value of z here, and we are just representing this w into x as a matrix multiplication. So b is a simple integer value. So we know that simple b is an integer value, whereas w is an array, right? Array or a matrix, and hence we need to do matrix multiplication or vector multiplication kind of a product here, and we can just add b. So this is what we are doing here. So the next step is to find the derivatives. Okay, so we have the y at values, and then now we can build these dw and the db formulas, and once you find these formulas, you can also build these two equations in order to update your weights, and that will be your final part. So the next step is to build the derivatives. So you can call this as derivatives or gradients. So dw is equal to, we know that it is 1 by m. So we are mentioning this 1 by m within this logistic regression class. So we need to mention it as 1 divided by self dot m. So we know that we need to mention it as self dot m into np dot. So dot represents dot product, or it's basically the matrix multiplication. Self dot x dot t. So we are taking the transpose and y at minus self dot b self dot y. So I'll just complete this and explain you what this means. So db is equal to 1 divided by self dot m into mp dot sum y at minus y, sorry, self dot y. Okay, so let's try to understand what we have done in these two lines of code. So I've just written these two equations, these two formulas here. So that's it. So it is nothing but 1 by m into y cap minus y into x, and db is equal to 1 by m into y cap minus y. So if, if you see this dw, so we have written it as 1 divided by self dot m. So we know that it is nothing but 1 by m into np dot dot. So we are taking we are taking product of x and y at minus self y, because we know that we need to find the difference between y cap and y, and we need to multiply it with x. Our x is nothing but this particular data. Okay, so the data without this y column is our x. So we need to find the difference between y cap. So y cap is nothing but the value you found using the sigmoid equation, and the y is nothing but the outcome column. Okay, so we need to find the difference between them, and we need to multiply it with x, and after that we need to multiply it with m. So this particular part, this y at minus self dot w represents this term. Okay, y cap minus y is represented by this term, and we need to multiply this with x. Okay, so that's what we are doing here. Self dot x, the important thing that we need to note here is we are taking transpose of x. Now you need to understand why we are taking the transpose of x. So I have already made videos on matrix multiplication, and the important point about matrix multiplication is that if you take two matrix and if you try to multiply these two matrix, the number of columns in the second matrix, which is this value, so the number of columns in the first matrix should be equal to the number of rows in the second matrix. Then only you can do the multiplication. So you can see the rule here as well. So the number of columns in the first matrix should be equal to the number of rows in the second matrix. So the resultant matrix will have the same number of rows as the first matrix, as the same number of columns as the second matrix. So what will be the shape of the resultant matrix is this. So 2 into 2, these two. So the important thing to note here is this value and this value should be same. So if you see this particular example, the number of columns in the first matrix is not equal. So this is not equal to the number of rows in the second matrix. So in this case, you cannot do the matrix multiplication. So it is basically the same thing. Okay. So let's try to find the shape of x and y at comma y. Okay. So what is the shape of x? So if you look at this, we know that the shape of this x is 769 into 8, right? So I'll just remove this. So the shape of y, just a second. So let's remove this, and yeah. So let's try to find the shape of x. So we know that the shape of x is 769 into 8, right? So 769 rows and 8 columns. And now let's try to find what is the shape of y. The shape of y is nothing but, just look at this last column. So it contains only one column, but it contains 769 rows, right? So therefore this will be our y. So the shape of this y is, so y shape will be 769 rows into one column. So it's 769 into one column. So if you just look at this, so this will be our y, and a to h will be your x. So the shape of x is 769 into 8, and the shape of y is 769 into 1. Okay, so now we cannot multiply these two. As I've told you, if you want to multiply two matrices, this value and this value should be similar. So that's the reason we are taking the transpose of x. So if you take the transpose of x, your x transpose will have the shape as 8 into, so when you take the transpose, your number of rows and columns will interchange. So you will have 8 rows and 769 columns. and you will take the y matrix as such. So your y will be 769 into 1. Okay, 769 into 1. Now as you can see here, this value and this value is a similar. Now you can multiply these two values. So the important insight or important takeaway is that you cannot multiply x and y directly, but you can take the transpose of x and you can multiply it with y. So that's what we are doing here. Okay, so if you come to this particular part, so that's what we are doing here. So y at and y will basically have the same shape, so that's why we are subtracting them. So once you subtract that, so we cannot multiply x and y as such, so we need to take the transpose of x, and then we are taking we are just multiplying it with this y at minus y. So we know that it is y cap minus y into x, and this is the same thing that we are doing here. The only difference is that we are taking the transpose of x, because you cannot multiply x as such, because there is some problems with the shape of the matrix, so we need to take the transpose. So we have successfully created our y at equation, and then we have created our dw and db equations, right? So the next thing that we need is this gradient descent equation, which is used for updating the weights, which is w and b. Now this is the last step, and it will be to write this w and b equation. And now let's write this. So this is our updating weights part. So updating the weights and bias using gradient descent equation. Okay, so the equation is w is equal to w minus alpha into dw, b is equal to b minus alpha into dw. So whenever you are mentioning w and b, we need to write it as self dot w and self dot b, as we are writing this within the class logistic regression. So self dot w is equal to self dot w minus self dot learning rate into your dw value. Okay, so just give some space here. Okay, so your db equation is self dot b is equal to the same, it is basically the same thing. So self dot b minus self dot learning rate into db. Okay, so these are all the equations that we need. So first we found the equations of this y at. Once we found the equation of this y at, we have used it in this dw and db equations, and after that we have substituted this dw and db equation in this updating weights equation, which is w is equal to w minus learning rate into dw, and b is equal to b minus learning rate into dw. Okay, so this is so the part, so this will be our part to implement gradient descent. So what basically happens is, if you look at this for loop, your for loop is runs the number of iterations we are mentioning. So if it is 100, this for loop will run 100 different times, and each time it will update the weights, and how it will updates the weight is based on this particular function. Okay, so first we are finding the y at value using the equation x dot w plus b, so that 1 divided sigma, basically the sigmoid equation. After that we are finding the dw and db values, and using these values we are updating the weight and bias value. Okay, so this is our next step, and finally once we found the optimum value of weight and bias, we can come to this predict part, and this part is to find the value of y given the value of x. So how we will do that is by creating again the sigmoid equation and then setting a decision boundary. Okay, so this will be writing the sigmoid equation and the decision boundary. So let's discuss what is meant by this. So as I've told you before, this y cap is what is the probability that your y value is equal to 1. Okay, and your y can take only two values, which is either 0 or 1, but your y cap value can have any values between 0 and 1, but the output that we want is either 0 or 1. So we just want to find whether a person has diabetes or not. Let's say that 1 represents a person with diabetes and 0 represents a person without diabetes. So your output value cannot be 0.2, or it cannot be 0.8, it cannot be 0.4, and so on. So we just take a decision boundary, and it is nothing but if your y cap value is greater than 0.5, then your output value should be 1. if your y cap value is less than 0.5, then the output value should be 0. So it is very simple as that. So your y cap value is nothing but the probability that y is equal to 1, and if your y cap value is greater than 0.5, you will take the y value as 1. If the y cap value is less than 0.5, your value will be 0. So that's what we are going to do in this last part of the code, which is define predict. Okay, so let's create a variable as y prediction, so or y pred. Okay, so y prediction represents y pred represents y prediction. So now we need to write the same y at equation, because we just need to find the equation of y at, right? So I'll just copy and paste this equation here. So y prediction is equal to 1 divided by 1 plus np.exp, and this is basically the sigmoid equation. So we are trying to find the equation of the value of y cap, and if the value of y cap is greater than 0.5, it should be 1. If the value is less than 0.5, it should be 0, right? So y pred, I'm going to write this as y pred is equal to np.var y pred greater than 0.5. In that case, the value should be 1 or it should be 0. Okay, so this is like a simple if condition. So it is similar to this, and I just want to return y pred. So let's try to understand what is meant by this. So we are just writing the same equation, the y at equation here, and instead of y at, I'm representing this as y pred, which is y prediction. So y prediction is equal to 1 divided by np.ex, this the same equation that we have here. So this y cap equation, and we know that if y cap is greater than 0.5, it should be 1, and that's what I have written here. So np.var, so your y prediction value will take the value 1 if your y prediction value is greater than 0.5, otherwise it will take the value of 0. So that is the use of this np.var function. So this is very useful for creating conditions. So here I have given a condition, right? If the condition is that the y prediction value is greater than 0.5, then your y prediction should get the value as 1, otherwise it should get the value as 0. So it is basically saying the same thing here. Y cap greater than 0.5, then take the value as 1. If it is less than 0.5, take the value as 0. So it is as simple as that. So when you give the value of x, so you need to mention the parameter x. Okay, because when you give the value of x, your final output should be 1 or 0. So your final output will look like, so let's say that we have trained a logistic regression model, everything is done. So let's say that we are taking all these 8 values. Okay, so we are taking all these 8 values. So when you give all these 8 values, your logistic regression model will find whether your output is either 1 or 0. So you cannot have any decimal values here, you can have only 1 or 0, the binary values, but the output that we get will have the values between 0 and 1. So in order to set that decision boundary, we are setting it as 0.5. If the value is greater than 0.5, take it as 1. If it is less than 0.5, then take it as 0, and that is what represented by this equation. Okay, so that is all for building the logistic regression model in Python. Okay, so we have created a class, so I'll just give you a quick recap. So I hope everyone is clear up to this point. Okay, so that is all that is related to building logistic regression from scratch. So what we have done is, so you can just come to these steps again. So the first step is setting the hyperparameters, learning rate, and the number of iterations, which we have done in the define init function. And after that, we need to initiate our weight value and bias value, and we have initiated with the value 0. After that, we need to update the weight and bias. So we will create our logistic regression function, which is the sigmoid function. So once we get that, we will build our gradient descent function, right? So gradient descent equation. So we will try to find the value of y at. After that, we try to find the value of dw and db, and finally we have written the equation for updating the weights and parameters. So this process will take place again and again. So the model will go through the data again and again based on the number of iterations that we are setting. So if you give 100, it will go through the data 100 times. If it is 2000, it will go through the data 2000 different times, and each time it will change the value of weight and bias using this gradient descent algorithm. Okay, so after the number of iterations, we will get an optimum model which has the best weight value and bias value. And once the model is trained from the data, you can use this predict function to determine the class of the data point. Class of the data points in the sense it is either 0 or 1, and for this we have set a decision boundary as 0.5. Okay, so that is all that we have done in our logistic regression model. Okay, so these are the equations that we have. So the sigmoid equation, the equation for z, and the gradient descent equation, w is equal to w minus alpha into dw, where your dw and db are given by these set of equations, and after that we have imported our numpy library, and then we have created the object as logistic regression. And inside this we have four different functions. So first is the init function, and fit function, which is used to fit the data to our model, and the third function is updating the weights function, where we have used gradient descent, and finally we use this predict function. Okay, so these are the four steps, and in the first step, in the init function we have declared the learning rate and number of iterations, which are the hyperparameters. And whenever you are mentioning the parameters within this class, you need to mention it with using this keyword self. So the second function is fit, and it is used to fit the x and y to our logistic regression model. And for that, the first step is finding m and n, where m is your number of rows or the number of data points that you have in your data set, or you can, and the value of n is the number of columns, or in other words, you can say it is the total number of input features. So we have found that by x dot shape, and then we initiated the weight value and the bias value as zeros. So weight should be an array, so we have created a numpy array with all the values as zero. Bias is a single value, and we have declared x and y, which is our data set. And then we have built this for loop in order to go through the data multiple times. And then we have set up this gradient descent algorithm, where we try to find the y at value, and then dw and db value, finally the formula for updating the weight and bias. Okay, and the last part is making this predict function, where we try to round the values. If the values is greater than 0.5, round it to 1. If the value is less than 0.5, round it to 0. So when you run this predict function, you will get the value as either 0 or 1. So this is how we can build the logistic regression model from scratch, and I hope everyone is clear up to this point. Please practice these codes, so then only it will be helpful for you. And in the next video, I'll show you how you can use this code, how you can use this logistic regression code in order to learn from a data set, and how you can predict new values. Okay, so that will be the next video, where we will try to implement logistic regression model from scratch. Okay, so that's it for this video, and I'll see you in the next upload. Thanks for watching.